So in this video, I'm going to go back to the theme of a dual-caustic Poncelet, but with a few new twists. So let's just consider a Poncelet iteration that starts from an outer black circle from point P1, and I'm going to pick a tangent from a first caustic, this red circle here, and reach point P2, then pick a second tangent from the second caustic, and then alternate, and I'm doing, I guess, six iterations here. So what I can do, for example, is move P1 around and see where this thing is going to lead me. Okay, so I'm actually interested here in basically finding a pair of maybe radii. So notice that these two caustics, for the sake of simplicity, are collinear. Their centers are collinear with the main center, the center of the outer circle. So I'm going to vary, for example, the radius of these circles of the two caustics in the hopes that maybe a particular radius is going to take me pretty close to P1 over here. So let's adjust this manually here. I'm going to place it over here. Let's see, is it close enough? Close enough, maybe 24, 23. Yes, and I'm looking here, I'm reporting the square of the distance between the first vertex and the seventh in the iteration. Now, much to my surprise, when you actually do this, when you actually run P1 across the outer circle, if you close manually, as I did, this sort of pseudo-porism, you're going to maintain the closure, okay, for all positions of P1 in the outer one. Okay, now you don't maintain that closure, that distance is not exactly zero, sort of it's not a strict Multiple-Porism, but it's a pretty good approximation of a Multiple-Porism. And you may say, okay, who cares? Why do I care about something that is not a porism? It's just an approximate porism. Now, the reason this is curious is because there's other choices. For example, here's an n equals. Let's take another n equals 4 choice, okay, which I've done manually here. So what am I talking about? I have two internal caustics as before, and I'm actually doing a different kind of iteration. I'm going to do the first one on the red, the second one on the red, and the remainder two on the green. Now the question is, can I close this polygon by tweaking the radii, right? So let's try to do that. Let's try to close that by tweaking the radii. And here we have a closed position. Now what happens if I now move P1 around? You can see here that I don't maintain the porism. In fact, I greatly deviate. The fifth and first vertex are not staying within close distance of each other. Okay, so compare this with the phenomenon that we're seeing before with n equals 6, right? The phenomenon before was this one, for example. I don't know if it was this one or some other related one, but here's an n equals 6. I was able to tweak the two radii in such a way that I can actually close the porism. Mysteriously, when you do this for this particular configuration, you get the pseudo maintenance of closure. Okay, so this maintenance of approximate closure is not a guarantee. It only happens for certain configuration. I'm not sure which ones they are. For example, let's look at another one that I prepared here. Here's an n equals 4 cross. So what do I mean by n equals 4 cross? I'm starting from P1, and then I'm actually running a tangent with respect to the red caustic, and then I'm from P2, I'm actually being tangent to the green one, but I'm actually picking the reverse tangent. So far, I've always picked the same clockwise or counterclockwise tangent with respect to the caustics, but there's always a choice, right? When a point on the outer conic is looking at the caustic, you can pick one that is sort of toward the left or toward the right. So here I'm actually doing P1 to P2, let's call this counterclockwise tangent to red, and then P2 to P3 clockwise tangent to green, and then I do another counterclockwise tangent to red, and then another clockwise tangent to green. I have this trajectory of program encoded by these two vectors here. So I'm picking the first, second caustic, and I'm going clockwise, counterclockwise, clockwise, counterclockwise. Okay, so this particular app that we've set up here has this sort of programmability, and I can pick an arbitrary trajectory type. But the interesting thing here is that I can tweak, for example, the distance between the centers. Let's try to do this, or the radius. For example, if I make this radius super small, not super small, but there's a particular radius that is going to make this guy close, like so. because I'm now going from P1 to P2 and then back and back and back 4 times. But the thing is, as soon as I move away from that closed configuration, I deviate. So P1 and P5 deviate. Likewise, I think I can try to do something like this. Let's see here. Can I try to close this guy as an, as an n equals 4, as we did before, I believe. No, not this way, but this way. Was I able to do this before? Let's see here. Let's move that to there. I thought I was. I thought I had an n equals. Okay, so maybe with this cross configuration, cross tangency configuration, I cannot. But I can do this in this particular way. So here's one that works, right? I start with P1. I pick a tangent to the red, counterclockwise tangent. Then P2, counterclockwise to green, counterclockwise to red, and counterclockwise to green. So I'm picking 1, 2, 1, 2 caustics and always picking a counterclockwise tangent. In this particular configuration, I maintain the pseudo-porism. So you saw that the cross tangent configuration does not. So there is this phenomenon where some trajectory or program choices maintain the pseudo-porism, meaning that the first and nth vertex, or n plus 1th vertex of the trajectory remain pretty close to each other. And what do I mean by pretty close? The distance between the first and last vertex are, 1/10,000th of the circumradius of the outer circle throughout the entire porism. Okay, for all positions of P1. Okay, let's look at another one. Let's look at this 8 periodic thing that I've previously set up. This one also maintains a porism, or the pseudo-porism, for some reason. Okay, so what am I doing here? I'm doing 1, 1, 2, 2 in terms of the caustics, 1, 1, 2, 2, and I'm taking everybody in the same tangent direction. Okay, so this one is maintaining the porism. What I mean maintaining the porism, there's a variable error that is really small compared to the, so it's less than 10,000th of the radius of, it's 1/10,000th of the radius of the outer circle over the entire sweeping of P1 on the outer circle. Now, of course, there's another, okay, I only have 8. Let's try to do an 8 here. Can I do that? No, I can't. I'm not set up for that. Let's go to the next one. Here's a 10 when I'm doing a 5, 5. So I'm doing 1, 1, 1, 1, 1, 5 tangents to a red, and 5 tangents to the green. Now look at what happens here. I'm obviously not close, so this is P11. It should be close to P1. But there's going to be a position, I believe. Oh, I thought it was, yeah, here we go. So at this particular configuration of P1, I close the porism. It's closed over here. But as soon as I deviate from there, I'm unstable. So here's another situation where I cannot hold the porism or the pseudo-porism. Let's look at another one. 12, 3, 3. What do I mean by 12, 3, 3? I'm doing 1, 1, 1, 2, 2, 2, 1, 1, 1, 2, 2, 2. So they're sort of well balanced. I'm using the two caustics in an equal way. I have previously chosen these radius, so this n equals 12 porism closes. And lo and behold, I maintain closure over all positions of P1 within 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 distance squared between the first and last. So that means that I'm averaging 10 to the minus 5 distance, or 10 to the minus 4 if you will, of the original circumradius, which is equal to 1. Let's look at a final one here. Here's 12, 2, 2, meaning I'm doing caustic 1, caustic 1, caustic 2, caustic 2, and I'm alternating in pairs. Before I was alternating in triples. Again, I'm being well balanced, and again, I maintain the pseudo-porism. Okay, so I guess there is a phenomenon here, sort of pseudo-Poncelet, approximate Poncelet, and it only happens for certain configurations. It's not always the case that you can actually maintain it, and the reasons of this kind of a approximate closure maintenance for whichever configurations are not clear. Anyway, this is what I wanted to show in this video. Thank you.